Hi everyone, we are on the Unit 3 Day 2 lesson, and we're going to be extending what we did yesterday in the Day 1 lesson, where we were finding the different forms of equations of a line in R2, and now we're going to be looking at the same type of thing, but just extending that into our third dimension in R3. So we're going from a much more familiar situation. You guys have obviously are well versed in lines in R2 to just extending that to something that's probably a little bit more theoretical and probably harder to picture in R3, but it's still going to follow the same kind of idea. So just to review, this is what we talked about yesterday with R2, and I do apologize, my color coding is a little bit different in today's note than what I did in the previous day, but hopefully you guys can follow along here. So we know that to get a vector equation of a line, we have to have a position vector, and that again gets us to the line, and a scalar multiple of the direction vector, which travels along the line. And that is true in R2, and it's also true in R3. We're just going to have, instead of a two-dimensional vector with an x and y coordinate, now we'll have that z component added in as well. So to find the equation of a line, we need 1 point and a direction vector. If we know that, that's the easiest case, because the point is again going to be our position vector. That's a point that gets us to the line. If we know a point, then the vector to that point gets us to the line. And the direction vector would obviously be the traveling along the line, the direction of that line. The other alternate kind of piece of information you could be given is 2 points. So you're going to use 1 point as the position and use both points, like A and B, for instance, to find direction vector from 1 point to the next. So this is not going to be really much different from what we did in the previous note. We've got 2 points, A and B, 2, 1, 3, and negative 1, 4, 7. And we want to find the vector equation of the line. So I am going to find a direction vector, AB, and subtracting the endpoints minus the start. So negative 1 minus 2 is negative 3. 4 minus 1 is positive 3, and 7 minus 3 is 4. So this is a direction vector. Remember, this is not unique. This is one possible direction vector. Maybe another person in the class found vector BA. Another person really doesn't like 3s, so multiplied them all by 5 and said it's negative 15, 15, and 20. That's still okay. It can be any scalar multiple of this. So this is my direction vector. And then I'm going to use either one of A and B as my position. I might just use B because I used, I believe in the previous note, I think I used point A. So this could be negative 1, 4, 7 plus T times negative 3, 3, 4. And T is any real number. So this is a point on the line. This is the direction vector going along the line. So you can get to anywhere on the line and add a scalar multiple of the direction vector of that line. And that is always the vector equation. Again, this is not unique. You guys will, I will ask that on a test you don't go, doing a ton of work to find some other random point just to make my life harder. But, you pick point A, you pick point B, it doesn't matter. There's an infinite number of possible correct vector equations for any line. And here we go. No, it is not unique. The position vector can be any point on the line. And the direction vector now, there still are an infinite number of possibilities for direction vector, but it can't be any vector. It has to be a scalar multiple of the direction vector that we found. So that was the direction vector AB that we found. And your direction vector for any correct answer for this has to be a scalar multiple of that. Just like in R2, we can also have parametric equations for the line. So this is the line that I found. I'm just going to recopy this from the part A. So that's my vector equation that I found in part A. The parametric equations, in R2 we only had two equations. We had an x and a y. Probably unsurprisingly, we're going to have a third equation here because we're dealing with R3, and that's going to be a z. So I'll have x equals -1 minus 3t, y equals, and maybe I'll color code these. So there's the -1 and minus 3t. That's okay. And y, we're going to take the 4 here and plus 3t. So you're just taking the x, y, and z components. And z will be 7 plus 4t. And we always just say t element of real numbers. So these are parametric equations for that. Now I have kind of a color-coded example of this, and I would really recommend not memorizing this. I think it's much easier to just find the vector equation. Remember this. This is like the number one most important thing right here, and it's not even an equation or anything. It's get to the line and then travel along the line. Those are the things that you really need to remember. First, you get to the line, that's a point on the line, and then a scalar multiple of the direction that goes along the line. If you remember that, you don't need to memorize like all of these. I don't memorize those. That seems silly to me, because I think that most people looking back here can say, oh, look, there's the x's, they go in an equation for x. There's the y's, they go in an equation for y. There's the z's, they go in the equation for z. And it's pretty easy to do from there. That I would never advise you guys memorizing this. I just remember that parametric means separate equations for x, y, and z. That's an important thing to know. If I say on a test, give me the parametric equations, you have to remember, oh, that word parametric, that means the three separate equations, one for x, y, and z. But how to get it, I wouldn't memorize the equations there per se. So here we are given, for example number 2, we're given two different equations of a line, two different lines. We want to know, are these the same line? So what things, remember, we can have any point on the line. When we talked about whether these were unique, it could be any point on the line, and that the direction vector had to be a scalar multiple. So this is probably the easiest to see. Are the direction vectors scalar multiples? Okay. And I think visually we can kind of say that yes, they are. So I'm going to say vector m2 is 2 times m1 because these are scalar multiples of each other. So they are parallel. Okay, so I know for sure that I have two lines that are going in the same direction. They have scalar multiple direction vectors. I've got a line there And I don't know if they're the same line yet, but each one I have a point. So I have a point and a direction vector. So I know that this one has point 1, 2, 3, and the second line, L2, we know for sure that it's parallel, but it's got this other point over here, 4, 3, 1. And obviously we're drawing these in R3. It's not, it's much more abstract of a diagram than what we would have in R2. So if we want to figure out, are these the same line, we know for sure that they're parallel. So they're either separate parallel lines that never cross, or they're the exact same line. And my argument would be that if they're the same line, then this point is on the red line and this point is on the blue line. Okay, so I might just pick the first point. So if they are the same, then this first point, 1, 2, 3, is on line 2. So my second line would have the point 1, 2, 3 on that. And that's something that we did look at in the day 1 lesson. Remember that we took those parametric equations and checked the x and y and z value and solved for the parameter t. So that's what I'm going to do here. I'm going to take L2 and create parametric equations. So x equals 4 plus 4s, and y equals 3 plus 2s, and z equals 1 plus 8s. And I'm going to check that point. I'm going to check is the point 1, 2, 3 on L2. And you could just as easily have checked whether this point 431 was on L1 and written the first line as parametric. That would work fine too. So I'm going to sub an x value of 1 in here. So bring the 4 over and subtract. I get negative 3 equals 4s, and s equals negative 3 over 4. So I would need these s's to also equal negative 3 over 4. So I'm going to sub those in and check. So putting in a 2 for the y value. 2 minus 3 equals 2s. Negative 1/2 equals s. So already I know that this is not going to work because they would all three of them have to be the same. I'm going to keep going and just show the work of finding the z though. I've got 3 equals 1 plus 8s. 3 minus 1 equals 8s. And 2 over 8 equals s, or 1/4. So I have different s values. Even if I had 2 the same but the third different, it would still be a no. They would all have to be the same if that point was on the line. So we could say therefore point 1, 2, 3 is not on L2, so they are parallel. But not the same line. Oh, so they are parallel, but not the same line. So that's a way of checking. It is a little bit tricky, right? Because we have these equations and they're not unique. You can have infinite number of possible representations of these equations. And how can you know if two people have different equations? It might mean the same line and it might not, and you really do kind of have to do these calculations to determine that. The last type of equations in R3, we're not going to have the Cartesian equations in R3, or the scalar equations that we also called those. We are going to have something different called symmetric equations. So what we're going to do for symmetric equations is solving those parametric equations of a line for the value t, and then setting them all equal to each other. Now in R2, we had two things that were equal, so we could cross multiply and simplify, but now we're going to end up with an x piece and a y piece and a z piece. So it's going to look like kind of one of those triple equations like the sine law sort of, and we won't be able to cross multiply to solve to make a nice unique equation. So first step here, we have a vector equation. R equals 135 plus t times 1 negative 2, 3. We're going to find the parametric equations, and that's just looking at the x, y, and z components. So x is 1 plus t, and y is 3 minus 2t, and z is 5 plus 3t. And t is any real number. Okay. To get the symmetric equations, we're going to take these three equations and solve each one to put it in the form t equals. So x equals 1 plus t. I'm just going to recopy them and write them horizontally so that I can more easily solve each one. It'll just give myself a bit better space here. So here, solving for t, x minus 1 equals t. Solving this one for t, I'm going to get y minus 3 divided by negative 2 equals t. You can use more steps than this if you want. Here we've got z minus 5 divided by 3 equals t. So I'm bringing the 5 over and dividing that 3 down. So if I have these three different equations that all equal t, it's just like what we did in R2 to find that Cartesian form. I can set them equal to each other, but like I said before, we're not going to be able to cross multiply because I actually have like a triple equation here. So here I've got an x part, a y part, and a z part. So there's no way to make this a simpler equation. And it does sort of kind of remind me of the sine law there, where you have three pieces. We know that they're all equal to each other, but we can't simplify that anymore. So this is called the symmetric equations, and that's something that only exists in R3. Those are not a type of equations that we see in R2. So again, this is the general form of the symmetric equations. I hate the idea of memorizing this because really from the vector equations, it's not too hard to find this, and I feel like memorizing all of these letters and subscripts is just gonna, for most people, like bog your brain down too much and get you away from really understanding, because this was not hard. To write separate equations for x, y, and z, solve each one for t, and make them all equal to each other. It was like 3 steps. So that's how you get the symmetric equations. And again, the thing I want you to remember is symmetric equations means like the ones that look like the sine law, where they're all equal to each other. I would very much advise against like memorizing that specific equation. I suppose if you did, then right from the vector form, you could pop it right into the formula there, but that doesn't seem like a good use of memory space in your brain. But maybe you have a great time memorizing formulas, and then if that's the case, then you go for it. So this one, we're asked to write symmetric equations for a line through these 2 points. So whenever I have points given or information given, I always go in this order. I would find the vector, then I would find the parametric, and then I would find the symmetric. And I suppose if you're a memorizer and you did memorize that formula, you could just go right from the vector equation and skip right over. But like I said, I don't have that memorized, and I don't feel like it's worth it for myself personally. So remember that the vector is position and this is get to the line. Plus t times direction. And the direction is move along the line. So I need a position, which could be either one of these 2 points, and I need a direction. So I'm just going to find direction vector AB, because that's the direction of this line, goes from A to B. So I'm going to get that direction vector by subtracting. So -3 minus 2 is -5. 2 minus 1 is 1. 5 minus 5 is 0. And then that's my direction vector. So now going back to the vector equation, always have R as your resultant. If you need to make multiple line equations, you would subscript them like R1, R2, like that. So a position vector could be OA, getting to point A, 2, 1, 5, plus T times the direction vector, -5, 1, 0, and T is a real number. Okay, so this is the vector form. The next step I would do is to write out your parametric equations. So that's the x, y, and z. And since I know that I'm going to have to solve, normally I write x equals y equals z equals kind of one on top of each other. But I know I need to get the isolate t in each one. So I may write the x, y, and z going across just so I have space below to solve for the t. It doesn't actually matter which direction you write those in. So here x equals 2 minus 5t. Y equals 1 plus t. And z equals 5, and then there's no t's. So plus 0t I might put in there. Now this is a little bit of a special case when we have a 0 in there. I'm going to solve this one for t. So x minus 2 over -5 and y minus 1. And we just get z equals 5. So sometimes that really throws people for a loop in terms of what do? I can't solve for t because there isn't a t in that equation. And that's okay when we do our, oh, whoops, this is, sorry, both equal to t. When we do our symmetric equations, we would write x minus 2 over -5 equals y minus 1, comma, z equals 5. So this one is actually an equation in 2 dimensions. You could get a Cartesian equation here, and the z value would be a constant of 5. Unlike the regular R2 equations where the z value is just 0 and it's right on the xy plane. This is on the plane z equals 5. So this line would be parallel to the xy plane, but just moved 5 units up in the z direction, and that's where that line would go. So if you get one that's a constant, you just add it in, and that's fine. This is the opposite, last example here, and here we're asked to get from this symmetric equations back to the vector. And again, I use that parametric as a middle ground. So remember when, just gonna pop the previous one up here, that I had solved here for t equals and then set them all equal. We're gonna go backwards. I'm gonna take the 3 pieces and make them each equal to t, and then isolate to get the parametric. Okay, so we would know that x plus 1 over negative 4 equals t. Y minus 5 over 9 equals t. And z minus 7 over negative 1 equals t. So this is just rewriting. And then I'm going to solve these. Normally we had them x equals y equals z equals, and we solve for t. Now we've got t equals, we're going to go the opposite direction. So I'm going to solve this one for x. So multiply up the negative 4 and bring that 1 over. I'm going to do this all in one step, but you don't have to. So it's going to be negative 4t and then a minus 1. So minus 1 minus 4t. And multiplying this up, I get 9t. Bring that 5 over, it'll be positive. Y equals 5 plus 9t. And then z, I'll bring the 7 over, so it's positive. That 1 multiplies up the negative 1. So z equals 7 minus t. And again, t is a real number. So then, and I don't know that we've done this too much yet, we need to separate out, there's the pieces of the position vector getting me to the line. Then I need to find the pieces of the direction vector. So kind of taking this, normally we take it and break it up into the x, y, and z components. Now we have the x, y, and z components, and we want to put it back. That this resultant vector would have a position of negative 1, 5, 7. And then which ones are multiplied by t? It's negative 4, 9, negative 1. So those are the three forms of equations in R3 for equations of lines. It's the vector, the parametric, and the symmetric. There's no Cartesian equation in lines in R3, but you should be able to convert between any of those different forms.